are these representations. And the maps are all possible homomorphisms. They don't need to be all possible homomorphisms. These are objects. That's not so beautiful. There's some different color stroke somewhere. Maybe this one. Here's some. Yeah. So right. So these are the objects. And these are the morphisms. The fact that this is the basic, this makes this this has a structure of tensor category, which Pasha mentioned, and with this category is symmetric. There's a basic thing that if I flip two factors here and two factors there, that is a map. Right? There's like S2 can permute these factors. And so then it's a simple observation, goes back to Hermann Weyl, that this category knows everything about your group. It knows what the group is, particularly it knows what the group is. And the reason it knows for the group is because I can consider just, so if I consider, let me add 4 terms here. And if I just look at G, so I'm looking at Sn invariance in Holmes. So let's say I do it maybe Vd to Vd Sn invariance, Sd invariance. What is that? It's some algebra, but what does this algebra? So what does this say? What does this guy say? It's, well, what is home from Vd to Vd? Well, that's just, so home is like have a dual space going to that space. So it's like saying I'm going to take V dual tensor V, and then I want the S, I want to take this symmetric power of that, right? That clear? And so these are just polynomials on D by D matrices, or on n by n matrices. Namely, these matrices. This is dimension V is n of degree D. Okay. So if I know all these maps, in particular, I know all G invariant polynomials on matrices. Is that clear? And if I know all G invariant polynomials of matrices, these are just so this means there's a map, the factorization of GLV. It acts. There's an action of G, so this goes to GLV mod G. Okay. These are the coordinates on, there's a free action of G on GLV. And the invariant polynomials are the coordinates on this quotient. Because the fiber over the identity here is the group G itself, so we know what the group is. We can really write the equation of the group if I know all this invariance. And you think about it, what does it mean? What does it say? For example, if I have SL, then means in the nth wedge there is an invariant vector. If you think about it, it's just really equation of the group. If I think about orthogonal or simplicity group, it says in the square of my tensor space there is an invariant vector. If I think about what it says, it's just really equation of my group. But it's very general. So if I know this category, then I know what the group is. I know everything. And maybe one takeaway from this, it's typically easier to think about categories than to think about equations. Okay? So This is where we will see examples of that later. Now we want to make it quantum. So now it has to be whatever, has to become quantum. So means something in this picture has to give. And what is the only, everything else was like, had like, whatever. In this picture, there's one concrete object. Everything else was just fluff. And it was only one object, like, actual mathematical object, namely the symmetric group. So when we make this stuff quantum, then the only and the main difference is that if I now take, so when I write the space with itself, but you can imagine that your space is, in fact, if your space is like a direct sum of some other spaces. If you have two different spaces, you can consider it a direct sum. So in direct sum, there will be the cross term. So you can just, when you talk about one space, you might as well talk about many spaces. So maybe I'll just start talking about many spaces. So in the usual story, just the permutation of factors, that was a morphism in my category. Right? If I permute the two factors, that was a G-equivalent map. And now this is the only place it can give, and it will give to, so maybe I'll give myself more space here. So V2 and V1. And there will be new morphism, which is need not square to 1, therefore I have to really pay attention to overcrossing or undercrossing. The morphism need not square to 1. There's a new guy which is called the R matrix. Okay. And we will require this R matrix to satisfy. So then you can ask, well, the three factors will be, so then when you have three tensor factors, then you can have, then you have three ways to permute the factor, two ways to permute put the factors in the opposite order, and we'll just require for simplicity that previously they were just equal, and we require they're equal again. That's going to happen. That's going to happen anyway. So we'll just, okay. So then this is satisfies. So this finds Young-Baxter. And now the next point I want to make is that in this setup, the kind of reconstruction I was talking about is typically much, much easier than what I just explained. Because you see, when it was symmetric group, it was like one size fits all. Like all groups were served by the symmetric group. Right? So we didn't have the mean. It's like, but as soon as they go quantum, each one has its own separate need. Each one of those groups will have to require its own separate R matrix. It's not like one R matrix is going to serve several groups. And so what you do is that maybe the reconstruction theorem uses, well, sorry, not the reconstruction theorem. If you want to reconstruct a hopeful algebra whose category of representation is this category, it's super easy. So the way you do it is like this. So you so then so suppose I have now. Well, let me switch to the situation. I have many different spaces. I have a collection of ways to braid them all. I mean, that's what happens anyway for Nakajima varieties. Suppose I have several vector spaces. It means G sits, my quantum G will sit in kind of a product of GL kind of VI. But these are not the Nakajima variety VIs. This is just some representations VI. Right, so how I'm going to do it? So I'm going to act. So I have some tensor product, maybe V1, V2, V3, V4, and I want to construct an operator in this product. So what I give myself is give myself an arbitrary auxiliary space. So I'll just put some line here so that we don't forget that this is auxiliary. Denote that V is 0. And I take the R matrix that braids them. So maybe I'll you don't need to write it like this, but maybe for the visual kind of effect, I'll write it as if I really previewed this. So the R matrix, once you have the R matrix defined on the generators, you just by fusion extend it to meaning. What does it mean by fusion? Means I have this line and it's just gonna cross all these lines. So it's just a product of our matrices going. So that's the R matrix of what we have here. Right? It means once you have R matrix on generators, then this procedure defines R matrix for any tensor product. And then if I want an operator in this space, all I do is I take an arbitrary matrix element here in the auxiliary space. So in the auxiliary space, I take an arbitrary matrix element in the auxiliary space, gives me an operator here. Right. This is some operator that and what I'm going to say, this is some operator so this means for every choice of auxiliary representation and for every choice of physical space, I get an operator for every choice of matrix element in the auxiliary space. No, you get the map from every matrix element here. You get the map from here to there, and these are the operators. Now the R matrix will braid these things correctly, because what does the Young-Baxter equation say? That if I are to braid these guys further, then by Young-Baxter I can bring this braiding here. So that will be saying that these operators, these tensor products really are braided by my R matrix as claimed. Right? So what is the analog of commutation relation in my algebra? What is the product of two operators like this? The product of two operators like this, it means I need to take one more copy, maybe V0 prime, derivative of 0, some other number. So I take another copy of V0 prime. And then, so this is kind of extend my auxiliary space to have two copies. And the new matrix elements, because they're just matrix elements of tensor product, they are products of operators. Right? So the products of my operators are matrix elements in a bigger space. And there's a commutation relation between, yeah. Oh, right. So this is easy. This is integration by parts. And there be a commutation relation. What are the commutation relations? That if I were to permute these two guys, I might as well by Young-Baxter bring it here. That's the commutation relation of my operator. Right? And now, it's a strand which is kind of like a double strand. You just increase the multiplication of operators, just increase the size of the auxiliary space. And then the Young-Baxter equation in the auxiliary space, that's the commutation relation for my operators. It says, what do I need to do to put them in the opposite order? That clear? Now, suppose, and so maybe just for kind of impact, maybe add triple guy here. No, double guy. So now we'll have to do all this thing again. So it'll be 0, prime, double prime, and then here. Now suppose I have some relation in my category, some actual relation in this category. And now what does it mean? That means that now suppose the R matrices leave, there's some, maybe there's some actual non-trivial home between this space and some other space, or maybe this space in itself. Right? That would mean that some matrix element of this operator vanishes. Right? I mean, what does it mean that there's this tensor? What does it mean that this tensor product somehow decomposes? It means that some matrix element of this R matrices vanishes. Right, clear? But then I can read, so this is kind of extremely point-to-point, that every relation in this category automatically gives me relation in the algebra, because if I have some relation on this side, if some matrix element of R matrices vanishes, then I can use the same relation on the auxiliary space. I mean, just permute the roles of what's physical, what's auxiliary. And that's a relation in my algebra. That clear? So again, suppose what does it mean? So when we were talking about the ordinary group, what does it mean that the space, that this tensor product breaks up? It means breaks up into, say, reducibles. What does it mean? It means that in some basis, I can choose a basis such as my such as the basis of this tensor product, such as my group elements only act here. Right? Means the action of my algebra, if I take matrix elements in where they're not, well, let's say, let's be ignorant about semi-simplicity. Let's suppose there's some reducibility. It means some matrix element of the action vanish. That's what reducibility says, right? But then, if I have something, if R matrices, so I'm just saying, consider the algebra of operators generated by all R matrices. This is the algebra of my operator, the matrix coefficients of all R matrices. Suppose there's some reducibility in this tensor product, means some matrix element of this vanishes. Right? But then this means that if I exchange the roles of what's physical, what's auxiliary, means there's some combination of operators that is identical to 0. It's a relation in my algebra. Right? Because, right? There's a matrix element here defines an operator here. If I take a matrix element here, it defines kind of an operator there. And so any kind of any decomposition in my tensor category gives me automatically a relation in the algebra I want. That's clear? And tautologically, well, maybe it's an exercise to actually write down what is the coproduct. What's the actual coproduct? That's a, and maybe it's a tautology. Maybe you should just write it down in the exercise. Anyway, that does define a Hopf algebra. Somehow this is somehow not new in math. This is how people, before quantum groups were named quantum groups, this is what people did. And then people took like an axiomatic approach to quantum groups with generators and relations, and then somehow, but then if you ask my opinion, well, I know this is being recorded. If you ask my opinion, like maybe let's go back to the first lecture. The very first lecture of this, well, not the first lecture of this school, but maybe the first lecture of this week, right? We said, okay, there's Nakajima variety and some quotient, some group, some variety by some group, right? Like in the old style algebraic geometry, like before Hilbert, what would that mean? That I would actually have to write down all the generators of the algebra of invariants, and figure out all the relation between these invariants. And then I say, well, this quotient is this variety presented by this, the generators will give me kind of coordinate, and the relation will give me equations, and that would be what? That would be the presentation. Yeah. Raise your hand if you think you'd be able to write this down, or like recognize the Hilbert scheme if presented by computer to you in this way. So I think so. Writing out relations, actually writing out explicit relation, I consider it a waste of time. So because it's, I mean, this never, unless it's something extremely beautiful, I think it's, I mean, we never do this for commutative algebras, for algebraic varieties. We never actually bother for an interesting variety to write down all equations that is, like one of my friends once was asked, well, can he write down all the equations defining moduli spaces of curves? He said, well, that's a question. What would I feel like if I shoot myself in the head? So, but really, if you write down the Hilbert scheme of points as defined by actual equations, that's just increase carbon footprint for no good reason. So so anyway, there's some whatever relations is satisfied. Usually if you have a category like this, generating morphisms are given to you. If you think, I mean, it's not, I mean, the category may be complicated, but the morphisms that generate all morphisms maybe not so, they very often, if there's finitely many of them, they're usually given to you. So you don't have to, I mean, that is enough. If you know what morphisms generate or morphisms in your category, that's enough. You don't have to think more. And so, right. So now how are we gonna? So now the question is, so we have solution of so point is that solution of Young-Baxter equation, and I'm not gonna use the chalk because then I'll have to erase it. But imagine there's an arrow going from here to there. So if I have a solution of Young-Baxter equation, then I have a then it means I made something a module over a quantum group. So if I have a solution Young-Baxter equation for something like this, it means I made all the spaces modules over a quantum group. Okay? So okay, now let's talk about Young-Baxter equation. So and we will do it with the spectral parameters instead. Right. When you have a spectral parameter, it means you have, when you take matrix coefficient, you don't get a number. You get a function. And that function you can expand, for example, if it's a rational function, you can expand it around 0 and infinity and get actual operators. If it's an elliptic function, then it's a separate discussion what you're going to do. But basically, if you have Young-Baxter equation depending on a variable, then you're going to get something which looks like representation of a group for the simple reason that your matrix coefficients already will have a variable in that way, but that variable is that loop variable. So you get like matrices depending on a parameter. Right. So the way Young-Baxter equation usually written is something like this. So this is where I always mess up, but it's something like this is equal to, let's see, that's a challenge. So let's see. Now I have to get the triangle look the other way. So all right, so here it goes. Did I succeed? Yeah, I think so. Right? And so what is this? What this usually I mean, one interpretation is that if this was the space and this was the it doesn't really matter. Nothing goes back in time, so better time goes here. So we sit in space, in one-dimensional space, and there's one-dimensional time. And there are some particles with velocities or rapidities or however you're going to call it that scatter. There's some interaction, and that and then the spectral parameters are really kind of the velocities of this too. and then and then the and then there's some in principle some triple interaction which we can factor into double interaction, and it doesn't matter in which order it happens. Okay. There's some. Everybody seen a picture like that? Well, you can see it now. And so now imagine we're observers. We sit in some space. We sit in some space in time. We just sit quietly. And just let time go by. And then instead, let's look in the space of momenta. What's going to happen is that as we vary the momenta, this is the plane. By invariance, I can only talk about the differences of momenta. This is the plane of U1, U2, U3 modulo 1, 1, 1. And then this is what will happen? That we would see particle come in different orders depending on. We'll see and see when one particle blob flies by, another particle flies by, third particle flies by. Right? So if we're at some generic point, we'll see them non-interacting. There's some vector space V, whatever the space is V1, V2, V3. That we'll see at a generic point. However, if we look when the momenta are exactly aligned in a certain way, then at our point we will see sometimes we will see them. We will see the actual. So the possibilities are when you have two of them actually interacting, or three of them actually interacting. So you can imagine that at the generic point you see them non-interacting. And then here, where this is where U1 is equal U2, then this is U2 is equal, this is where U1, this with 2 is equal U3, and this is where U1 is equal U3. Then at a special point, you'll see actually at a special point, you'll see some kind of bound state of this 2. Tensor V3, and here you'll see, some bound state of that too. Tensor V1, and then occasionally you'll see all three of them actually collide in front of your eyes. Eventually you'll see like the big blob when all three collide. We can think this is just insertion. You have some insertions of some operator, and in momentum space, this is where you insert them. And you can sometimes insert them, usually insert them at a distinct point, but sometimes you insert them sometimes you insert them in the middle, then you actually see the interaction. And so the pictures really should not be Young-Baxter equation. The picture should really be a picture of you have an arrangement of hyperplanes like this, where all possible collisions can take place. And then instead of crossing, so maybe U2. I won't have space for spectral variables. I'll just write them in a different order. So V2, V1, V3. Instead of going from here to there, you in fact you first go to the wall, and then you go off the wall. And that's really what should happen. And that's what I'm driving at. So if you think about Yang-Baxter equation, it's much better to think every R matrix as being factored into 2. First these two guys come together, and then they come apart in different ways. That makes sense? And then Yang-Baxter equation is just consistency of all them coming back together. In other words, there also should be, so what you should really have is a collection of maps, vector space and then maps. Like these 3 can come together here. So instead of Yang-Baxter equation being just a relation between kind of open cells here, you should have for every strata of this picture, you should have a map from this open guy going to the boundary, this guy going to the boundary, and this guy going to the boundary of itself. So there's this really. Yes? You can arrange it that it goes through the center. You can imagine that this is when it gets very small. From far away. What this picture is really is a triple interaction, which in fact happens as if they're only double interaction. So that's what it's. And there's some triple interaction which in fact can couple. So there's some. In other words, what does it say? There's some triple interaction, meaning like if I wanted these guys to exactly, or maybe these 3 guys, if I want to exactly reorder, means like in this picture, means appear in exactly the opposite order. I can think of this as going through this middle. They all 3 collide, and then they all 3 come on the other side. But Yang-Baxter equation says that instead you could have collided them, 3 of them like that, or 3 of them like this. Right? That's what? Yeah, they're not. So the point is that they will be not isomorphisms. This is why there will be poles. There will be isomorphisms exactly when there's some. This maps will have. This maps will fail to be isomorphisms when exactly something like this happens. Okay. Well, maybe one more time. What I propose, or now I have to somehow wrap it up. What I propose is that instead of thinking of Yang-Baxter equation, which is really a representation of like the fundamental groupoid of the complement of this hyperplane. Okay, this is just take this hyperplane and associate some vector space to every strata in this arrangement, meaning something to the middle, something to the open cells, and then associate maps that are basically isomorphisms, but these are regular maps. And then the fact that there's a pole in the R matrix is the fact that this is, if I want to take a map and the inverse of another map, that might have a pole. The inverse of a map can have a pole.
If I just know what's going on with the complements of the hyperplanes, yeah. I can construct what's going on with the hyperplanes if I know all the monitoring hyperplanes.
So maybe, even if you don't know anything, then I'm sure you can construct anything out of it. But what I'm proposing is a simplified procedure. Instead of trying to construct it all at once, construct first a half of the R matrix. And then this would be so in the setup that Pash is talking about, it worries him a lot that R matrices have poles. This map don't have poles. These are regular maps. So they're just they fail to be isomorphisms on some hyperplanes. And so if you consider if you want an actual kind of wall crossing, which is this map times the inverse of that map, that will have a pole. But that's, if pole worries you, then you should not think about the inverse of the other one. Okay. So now we're supposed to produce a picture like this from some geometric consideration. And where have we seen a picture like this before? Well, I don't know if you've seen or not seen this picture like this before. But I remember when we had this, this is a picture I drew some lectures ago, that if I take we were talking about K-theory of, or cohomology. So let's say take the K-theory of, since we talk about Grassmannian, let's just do this Grassmannian. So we take K-theory, covariant K-theory of T star, or sorry, the disjoint union. There were some wrappers that I guess are gone now. So the K-theory of covariant K-theory of the union from K goes from 0 to n, T star Grassmannian Kn. And over this, we had an action on this. So not on this, but on the Grassmannian. There was an action of GLN. Right. In GLN, we need, this would be, these variables will be equivalent variables. And so we need, they will take variables here. So we need something depends on 3 variables. So we'll just need a subtorus. We'll take a subtorus of the form. There's a variable that's called U1, repeated some number of times, maybe n1 times. Then the variable called U2, repeated some number of times, n2 times. And then the variable called U3, repeated some number of times, n3 times. And so then, where n1 plus n2 plus n3 equals n. And so we discussed that this is some ring that sits, so some ring that defines some algebraic variety that maps. So there's some spec of this K-theory is some algebraic variety that maps down to the space of equivalent variables, in particular to just the space of triples U1, U2, U3. And what are the fibers? What are the fibers of this map? The fibers of this map are the K-theory of the corresponding fixed locus. Right? So if I take the Yashin, help me. So I'm just going to draw exact same picture. So if U1, U2, U3, I mean the scalars act trivially, so I can mod out by the same. It's only the differences. It's only the ratio of these variables matter. So when U1, U2, U3 are generic, the fiber is the K-theory of the fixed locus, which is with the, yeah. This is a ring, means its spectrum is some algebraic variety. Yeah, and that it maps down to these variables. And just these are some coordinates here, so there's a map from this guy here, and the fibers are the K-theories of the fixed loci. So what sits over the generic point is the K-theory of the product of 3 Grassmannian. Maybe let's abbreviate. This is too much, so let's have abbreviation. TGN is cotangent bundle, is this disjoint union. Otherwise it's just disjoint union for K goes from 0 to n, T star Grassmannian Kn. So over generic point, I get the K theory. I'll just write the space itself, and then you can take it. We can take the K theory. So what says the K theory of And then over generic point, I get CG N1 times CG N2 times CG N3. That's what I get on the over generic point. Then if U1 equals U2, then here my fixed locus jump. So here I get CG of N1 plus N2 cross CG N3. This is what I get on this wall. And in the middle, here sits my CG of N. That clear?
Did the UIs take values of C star?
Yeah. But that's okay, that's a universal cover. cross, and then I look at the normal bundle, will be some attracting directions, and some repelling directions. And the general trajectory will go down. And it's, in fact, and so I'll have two correspondents, the attracting manifold and the repelling manifold. If I take the attracting manifold, its closure, you might take the upper point. So, but at which point it becomes a repelling manifold then. And we'll do a new tracking direction. So you can think, so you can consider kind of, you can have the attracting manifold. Then, so there are two choices. Attracting or repelling, I'll just try to attracting manifold. This is attracting manifold, this is some sub-manifold in X, A cross X, that consists of pairs of points, some point X, and some fixed point called F, X and F, such that the limit of A, so this is my torus, this is an element here, it's A times X equals F. This A equals to 0. So there are two choices like that. So they, what? Say again?
It's the factors of the path.
Oh, right. And so this is like, in fact, it's Lagrange's submanifold in this product. Kind of easy to see. The main issue with that is that, okay, it's a manifold, but it doesn't define for us a correspondence. It's not, for example, it's not closed. It's an open stuff. And the correspondence is by definition the actual homology class or rotating class of the product. Right, so to define something on the product, we need like actual cycle on the product, not of something which is locally closed.
Why is it closed?
What?
Why is it closed?
Well, because you see, I had trouble. I had to switch the colors. So that will contain. Right? This is the closure of attracting. Hit something else, right? It's not close.
It's attracting for different points, right?
No. It's an issue. Right? I mean, it's not an actual issue. It's something you have to say. Right? So if I have an open submanifold, if I have an open submanifold here, you want to define actual correspondence. To define the actual correspondence case here, maybe you think, well, why don't I just take its closure? I'll be okay. Since I'm freely sharing your wisdom about algebraic geometry today, like the uselessness of equations, then again, my advice. I mean, okay, I'm an old man. I've made my mistake. You don't have to repeat my mistakes. But if you want to repeat my mistakes, never take closure. Because in algebraic geometry, you never know what's at the closure. I mean, it's a silly thing. I mean, besides, if you take the closure, you will, this stuff will not satisfy the equations I want. Because what you need to do is you need to take the basic equation I want to satisfy is that if I go to your map, what was the map? What's the stuff I want? What's the equation that we need for a young boxer? The equation we need for a young boxer is we need this kind of triangle to be even. This is what young boxer requires. The map from here to there compared to the map from here to there, the same thing. And if you take the closure, you will fail that. What? For the reasons that like the closure of a closure is not the it's not
not continuous. I mean, there's no. Right. I mean, like if you take closures in different orders, I mean, this stuff just not work.
Why do people take closure?
Some people
are stupid.
Some people like closure. This is what it's like a kind of phrase you hear in therapy. But anyway, taking closure is bad. And it is especially bad. So what would be the outcome of all of that? The outcome of all of that would be solution of Young-Baxter equation, in which the spaces are like the k theory of all these varieties. And the spectral variables are just really this variable. These are the variables. The actual variable is actual variable. It's really very variable. They live there, they think they're there. And then you can ask yourself, well, if you had, this would be what people call the trigonometric solution to Young-Baxter equations. When people think about k theory, there's the torus, and people classically trained think of the torus as being parameterized by trigonometric functions. And so this is, then you can ask yourself, well, can you get like elliptic solutions of Young-Baxter equations? And then taking closure would be really, really bad. I mean, if you wanted to find something in elliptic homology, yeah, then you really need a smooth management. I mean, it's just elliptic homology, you actually come from like borders and stuff, and you have to really work with smooth management. And then you go, well, maybe okay, if I have something singular, maybe okay, let me desingularize it, let me resolve it. The point is that the result, there's no, if you want to have a singular manifold, it doesn't define anything in elliptic homology, because different disingularization can be different answers. So anyway, taking closure is bad for a roundabout reason, but there is a way out. There is a way to define it, and in cohomology, there's a very easy way to define it. In cohomology, so I'll just give you the definition of cohomology, and then you can go home. No, stay here for the main attraction of this week, and then which is. But in cohomology, there is a very easy answer. In cohomology, all the spaces have a deformation. All the spaces have a deformation of the following kind. Remember we set the complex moment map, we set it to 0. But instead, you take the complex moment map and set it to some scalar, some scalar times the -1. That's a deformation of your variety. And what will happen with this deformation is this deformation will be a fine algebraic variety. And on a fine algebraic variety, you can never have a torus orbit at a different point. Because that would be, if this was in the closure of that orbit, it's actually P1. And in the final algebraic variety, there's no curves. And so once you deform, then this attractive manifold will have, after deformation, this attractive manifold will have to go like that. It will have to miss all the other points. And so after deformation, that stuff is closed. That defines a well-defined cycle. And you can take, so you have a cycle in the deformation, you can just take, if there's a canonical extension to central fiber, just take the closure of that cycle, that's canonical.
But taking closures is bad.
No, taking closure in algebraic geometry is better. Taking closure in real, it's a real cycle, it's not a K-theory thing. Yeah, so in algebraic geometry you don't take closure. In point set topology, it's okay. Sorry, should I sound inconsistent?
No, I'm very confused.
What?
I'm totally confused. That's okay.
No, anyway, if you have a cycle under the, if you have a cohomology, like an actual cohomology cycle in deformation, it defines for you something in the central fiber. It doesn't define, like structure sheaf of that doesn't define you a sheaf in the central fiber. But if you have an algebraic cycle, it does define you a cycle in the. And you can take this, and you see that this will have to be, this will not be what you think before. This will have like this guy, will have some, what's the limit of that cycle? The limit of that cycle will wrap this effect into something else.
Why doesn't this work in K-theory?
Because in K-theory there's no way to put if you're asking for, yeah, there are many ways to take a limit of a sheet. There's nothing canonical about it. Especially since maybe the more technical answer, you ask for a covariance sheet. It's especially bad if your group acts on the base of the deformation, which it happens here. Here you have the scalar takes values. The scalar is actually, since this is a moment map, the scalar actually scaled by a group that scales the scalar symplectic form. So this deformation is there's a deformation covariant, no, but the group acts on trivial on the base of the deformation, and then that's special. So but you see that this already tells you that you would be wrong to take the closure, because even in cohomology this is not the closure. You have to add some stuff that comes from the limits of this curve. But then this is, with this limit argument, then it's in cohomology, then it's kind of trivial to see that it's satisfied. And in K-theory, I'm looking for something else. Oh, now I'm good. Deep in overtime. No, it's a long song. Yeah, let's save it for tomorrow. Yeah.
If I could just ask a follow-up question. The picture seems to be that for the A-type Nakajima-Quiver variety, what you have shown us, maybe I at least understood the message, but it seems to be that Rosmanian type, which is the A-type Nakajima-Quiver variety. So is there any similar concrete description for at least other weekend type Nakajima-Quiver varieties?
So what I've proven to you is that the correct module of any Nakajima variety is a module over some Yankee. Or any at all. Because this would be the exercise which you're supposed to do is that if I take the framing torus of this kind, then the fixed loci are the fixed loci and the Nakajima variety of products of the Nakajima variety of the exact same type. In fact, this we replace TG by arbitrary Nakajima variety, that would be still okay. And this deformation that we deform this to a scalar that works for arbitrary Nakajima variety. Therefore, any Nakajima variety gives you an R matrix with it's kind of rational R matrix because it's cohomology. So it depends rationally with on this variable Q that takes value most that take value in the Lie they sit in the Lie algebra. So maybe exercise. Do this computation. Do the computation for TG2. TG2 is after what is it? It's a point union T star P1 union point. So TG2 is the union of potential bundles to Grassmannian of all possible subspaces in two-dimensional space. So it's that. And so what you have to do is the R matrix will have the form, well, nothing's going on with the point. and then something here. Depends on the variable u, that says u is the variable indicative 1, sorry, 0, and u is in without the 0. And then in here you have to find this Young's R matrix. You have to find h bar over u times the permutation. Yeah, there's sometimes something. Because that's not good either, because this is not going to be 1 here. It's okay, times whatever you need to make it 1 here. This whole scalar. Scalar is just so you know. Yeah.
So what was really your motivation for the definition of stable envelopes? Like, how did you figure it out? Is it really this kind of commuting property that you wanted to make work?
What did you feel? No, the actual story, what was the story? The story was that, so this guy, McKee and Samson, they said that this space, well, I guess Nakajima also said, the space should be like the quantum cosmology of this guy should be really this kind of box. Well, this is McKee and Samson. They said that the quantum cosmology of this variety should be like this really box-stir subalgebra in Yang. That's the thing. I failed, and then you can start. Okay, among all the classical. Then the question is, among all the quantum multiplications, particularly the classical multiplication. They turn on the quantum problem, just algebra, just classical multiplication. Because for that we know the eigenbasis in the fixed point. And so now if you want to figure out what is the actual spin basis and spin chain basis, then you have to figure out what is that spin. You know, then conversely in the spin chain basis you know the operators that this is too much answer. But anyway, in the spin chains are given. In the spin chain, you have like a standard basis of C2, and then you have these operators. You write commuting operators, and in the classical limit, they just can really diagonalize them. And that should go to the fixed point. And then one has to figure out, well, how do I conversely, like geometrically define that spin base? So once, if I define the spin base, then I'm done, because the R matrices really commute the spin base, which is right. So that was the question. What's the right definition of the spin basis in the original That's the question that the state lambda finds. All right. You guys need a break before the main attraction.